Hello everybody, I hope all of you are doing well. So in this concept talk, we're going to be looking at the idea of moment of inertia. Okay, moment of inertia. And of course, I'll be posting detailed notes on moment of inertia on your course page. Here, I'm going to just look at a basic overview of it, and then we will go on to working out some problems. Okay, so our aim is to look at the basic concept of moment of inertia and what exactly does it signify. It's a geometric property of a shape. Okay, so the moment of inertia is a geometric property of a shape. Okay, and it essentially tells us, or it's a measure of the distribution of the area of the shape about a particular axis. Okay, so in that sense, moment of inertia, and my shorthand notation for moment of inertia is MOI. Okay, so MOI is a measure of the distribution of area of that shape about a particular axis. Okay, so this is the basic definition. Okay, what we will be doing is we are going to be looking at area moments of inertia. Okay, so the MOI that I'm looking at, so we look at area moments of inertia. And this is also called as a second moment of the area. Okay, this is the terminology, and this is what you'll be seeing in mechanics of materials. In dynamics, you will also be seeing the term mass moment of inertia. But the basic idea is the same. If you're looking at an area moment of inertia from that perspective is a measure of the distribution of area about a particular axis. If you're looking at mass moment of inertia, then the moment of inertia is from that perspective descriptive of the distribution of mass about a particular axis. Okay, all right. So now we go to the mathematical definition. This is definition without any proof. I'm not providing the proof here. Okay, so the mathematical definition of area moment of inertia. Okay, and I wanted to underline, yeah, I didn't underline that, that's okay, I guess. All right, so I'm setting up a coordinate frame. Let's say that I have an XY coordinate frame right down here, Cartesian coordinate frame, okay? Trying to draw straight lines early in the morning is frustrating. I guess it's not that early now, but I started off early. Then I have, let's say, some arbitrary body, okay, that is sitting here. So some arbitrary shape, okay. Let's say that this is some arbitrary shape of area capital A, okay. And on this arbitrary shape, I'm going to look at an infinitesimal area. An infinitesimal area meaning a very, very tiny, small area. And let me draw it in the form of a rectangle. I guess it became a square, but well, once again, it's getting to be a circle. I'm sorry. So let me see. Got to be careful. Okay, so this guy here is an infinitesimal area. Okay, let me point it out. Infinitesimal means very tiny area element of area dA. Okay, so A is the total area and dA is the area of this infinitesimal element. Okay, so A is the total area of the body of the shape, and dA is a tiny area of the infinitesimal shape. And let's say that the location, since this is infinitesimal, right, then this is almost similar to that of a point. Okay, so this is equivalent to a point. Okay, but of course you will argue with me and say, okay, hey, a point does not have any dimensions, right? It does not have any, I'm sorry, geometry. But then you think of it as a very, very tiny area. This is approximately equivalent to a point. Okay, and I'm going to locate the um, area element from the origin, okay, which is defined as the following. So here is my origin O, and from the origin I'm going to say that, okay, the height of this area element is the following. This is some distance little y, and the location along the x-axis is some distance little x. Okay, so little x and little y is the location of the infinitesimal area element from the origin. Okay, then if I call the moment of inertia of the area A about the x-axis as I bar ix, okay, so let's say moment of inertia of area A about the x-axis, I'm going to call this as I suffix x, and then likewise the moment of inertia of area A about the y-axis, I'm going to call this as IY. Then the mathematical definition is the following. Ix is going to be given as an area integral y square dA, second moment of the area, and then Iy is going to be defined as the area integral x square dA. Okay, so this is an area integral or a double integral. Okay, this is a double integral, and they are both double integrals in that sense. Okay, all right, so this is the formal mathematical definition of the moment of inertia. And what is the need for defining the moment of inertia? Okay, so the need defining the moment of inertia Okay, this will be typically very useful from the point of view of stress analysis. Okay, so this is important from the point of view of stress analysis. Okay, so typically what you do in statics is you look at how to locate centroids and obtain moments of inertia. You look at centroids, locate and obtain the moment of inertia. Okay, then in mechanics of materials, you will see how to use these for stress analysis. Use the above info to perform stress analysis. Okay, so this is a typical need for defining moment of inertia and so on. Okay, now I'm going to look at what is called as the parallel axis theorem. This will of course not be proved. Okay, we can prove it easily. It's not a big deal, but I'm not going to be proving it here. but this is very important. Okay, so the parallel axis theorem. Statement but no proof. Okay, it doesn't mean that there is no proof. There is a proof, of course, but all I mean to say is I want to state it, and then but the proof will be subjugated to your Karman page. Okay, all right. Here is the basic idea. If we know the moment of inertia of a shape about its centroidal axis, then you can use the parallel axis theorem to obtain the moment of inertia of the same shape about any set of axes that is parallel to the centroidal axis. I'm going to write this down. Okay, so if we know the moment of inertia, if we know or can calculate moment of inertia of a shape about its centroidal axis, then by using the parallel axis theorem, we can obtain the moment of inertia of the same shape about any set of axes that are parallel to the centroidal axis. To the centroidal axis. Okay, this is the beauty or the power of the parallel axis theorem. Okay, so once again, statement is, if we know or we can calculate the moment of inertia of a shape about its centroidal axis, then by the use of the parallel axis theorem, we can obtain the moment of inertia of the same shape about any set of axes that are parallel to the centroidal axis. Okay, so here is the basic idea. I'm once again going to take my arbitrary shape from above. Okay, so let me just take this guy without any of the other things, I guess. Let me take all of it, and then I'm going to whittle it down to the things that I need. Okay, so here is an arbitrary shape. I'm going to get rid of all of that. Okay, cut that off and so on. Okay, now let's say that I locate the centroid of the shape. Okay, let's say that the centroid of the shape is sitting right down here, so this is the centroid C for the shape. Then I can set up a pair of centroidal axes. Okay, the centroidal axes, I'm going to call them as the following. Okay, so these will be called as X bar and Y bar. Okay, or XC and YC if you want to think of it that way. Okay, so this is X bar, this is Y bar. Okay, then let's say let's write down the following. Okay, so here C is the centroid of the shape of area A. Okay, X bar and Y bar are the centroidal axes. For that shape. X and Y, as you can see, are axes that are parallel to the centroidal axis. X and Y are axes parallel to the centroidal axis. Okay, now let's say that the distance between the X and the X bar axis is the following. Okay, I need a different color, so let's choose this color. So let's say that the distance between these two axes is a distance d suffix y, and let's say that the distance between these two axes, the x-axis here and there, is a distance d suffix x. Okay, so I may want to write this down a little better, so I'm going to scoot this guy and bring this creature up here, okay, so that we can see it better. And I'm going to scoot this up a little more and up a little more. Okay, and so this distance now I'm going to call it as d suffix x. Okay, so dx and dy is the distance between x and x bar and y bar respectively. Okay, so this is the story so far. So let's say that we know these things. Okay, so let's say we know how to locate C. Okay, then let's say that we also know the centroidal axis, and let's say we know the location of this, and all of these are known to us. Okay, so let us say we know all of these. So I know that, then I know that, and I know that, and of course I know that as well. Okay, so once I know all of these, then I can write the parallel axis theorem as the following. Okay, the parallel axis theorem says that if Ix bar is the moment of inertia, so if Ix bar is moment of inertia of area A about the x bar axis, Iy bar is the moment of inertia of area A about the y bar axis, then if these can be calculated, okay, so if we can calculate these, then the parallel axis theorem says the following. Okay, it says that Ix is equal to Ix bar plus the area of the shape times the distance between the two axes, dy square. Okay, and I don't want to write that star thing there, so I just say this is a times dy square, and then Iy is going to be Iy bar plus a times dx square. Okay, so this is the parallel axis theorem. And this is something you will have to remember. Okay, okay, and in this situation, Ix and Iy are moment of inertia about the x and y axes respectively. Okay, so this is typically what we have in terms of the parallel axis theorem, and our situation is we're going to be focusing mostly on rectangular shapes. Okay, so I'm going to use this theorem for rectangular shapes. Okay, so our focus is on rectangular shapes. Okay, so let us use the idea to find the moment of inertia of the rectangular shape. Okay, so let's say problem number 1. Okay, obtain moment of inertia of the rectangular shape of base B and height h about x bar, y bar, and the xy axes. I'm going to set up the axes. Okay, so first of all, here is the rectangular shape. It's a nice little rectangle. or looks like a nice little rectangle until I complete drawing it. Okay, then let's say once again, okay, so here is the situation. Okay, let me scoot this person down here so that it's all aligned with the lines that I have. Sometimes I'm being a little silly. Then I say, okay, hey, here is the x-axis and the y-axis. I'm just going to extend this and call this as the x and the y. So this is the y-axis, this is the x-axis. Okay, and then the total width of the triangle and so on is given to me. The base is b and the height is h. So this is the base b and the height is h. Now, where is the centroid of the rectangle? Of course, it's going to be right at its center, right? So the centroid of this rectangle, I'm going to say, is right at its center. Okay, so this is the centroid C, which means that I'm going to set up a centroidal axis here, which is going to be called as x bar and y bar. Okay, so this is going to be called as x bar. This is going to be called as y bar. Okay, then I mark the distance between these two axes. Okay, this is fairly straightforward to see, right? This is going to be a distance of h by 2. Okay, and this is equivalent to your distance dy, and this distance here is going to be b by 2, which is the same as the distance dx that we had marked in our earlier figure. Okay, all right. Now, before I go ahead and I calculate the parallel axis theorem and so on, or I use the parallel axis theorem, I'm going to use the idea of integration here. Okay, so look at this. Let me take a very small area element, okay, which I'm defining here. This is this infinitesimal area element within the rectangle, okay, which I'm calling as a dA. Okay, so this is dA, which I can give as a product of dx times dy. Okay, this is an infinitesimal area element. Okay, then what I can say is the following by the definition of the moment of inertia, right? So dA is an infinitesimal, dA is dx multiplied by dy is an infinitesimal area within the rectangle. Then by definition, Ix bar is going to be the following. This is going to be integral of the area y square dA, right? So this is going to give me Ix bar is equal to integral area integral dA is dx and dy. So I'm going to be integrating it between the limits, which are going to be the following. Look at this. The centroid is located right at the center, so things to the left are negative, things to the right are positive for the centroid along the x-axis. Similarly, things below the centroid is negative, above the centroid is positive. So the limits of integration are the following. Okay, so this is going to be minus h by 2 to plus h by 2, and then this is going to be minus b by 2 to plus b by 2 y square times dx times dy. And if you do the integration, you will end up having this as this is just a double integral. You can just do this very quickly. I'm not going to do that. It's 1 by 12 bhq. Okay, likewise I y bar is integral area integral x square dA, okay, which tells me that I y bar is going to be the double integral, same idea, minus h by 2 plus h by 2 minus b by 2 plus b by 2 x square dA. dA is dx times dy, and if I do the integration, this is going to end up being 1 by 12 hb cube. Okay, and look at the units for moments of inertia. For area moment of inertia, okay, the unit will be millimeter cube times millimeters, or meter cubes times meters. So it's going to be distance to the power 4, or meter to the power 4, or inches to the power 4 or feet to the power 4, etc. Okay, so this is essentially distance to the power 4. Okay, so these are the two things that I know so far. Okay, so from integration, by the basic definition and integration, I know that Ix bar is 1/12 bh cube, Iy bar is 1/12 hb cube. Okay, then use the parallel axis theorem. Okay, now this is the moment of inertia about the centroidal axis, right? So this we can say is the moment of inertia about the centroidal axis. Okay, now by using the parallel axis theorem, I can find the moment of inertia about the axis parallel to the centroidal axis. I'm just going to grab my figure from here and reduce its size and so on. Okay, guess I don't need any of that now. I'm done with that area. Okay, so I'm just going to bring it down here and reduce its size and keep it in front of us. Okay, so from the parallel axis theorem, I can say the following. Ix, which is about this x-axis, is going to be Ix bar plus area times dy square. Okay, so which means that this is going to be 1/12 bh cube plus the area b times h times dy square, as you can see, is h by 2 whole square. Okay, if you do the addition, Ix will end up being 1/3 bh cube. Okay, this is from the parallel axis theorem. Likewise, you can also do Iy is equal to Iy bar a times dx square, the distance between the two parallel axes. This is going to be 1/12 hb cube base times height times b by 2 whole square, or Iy will end up being 1/3 hb cube. Okay, so this is a simple application of the parallel axis theorem that is something quite useful to us. Okay, so these are the area moment of inertia. So let me maybe mark them down. So these two are the area moment of inertia about the axes parallel to the centroidal axis, using the parallel axis theorem. Okay, things to remember now. Okay, essentially these are the things that you'd want to remember if you have to use the parallel axis, if you have to use the concept of moment of inertia. Okay, rectangular shape. The base is b. The height is h. Okay, then the second thing, and the area is a base times height, of course, b times h. Okay, the second thing you got to remember is that the moment of inertia excuse me, of the rectangular shape about its centroidal axis. This is something that you got to remember. We just derived it from integration. Okay, it was derived above. Okay, this is something that you'll remember as Ix bar is equal to 1/12 bh cube and Iy bar is equal to 1/12 hb cube. And the third thing that you'll be remembering is the parallel axis theorem. The parallel axis theorem, you will have Ix is Ix bar plus a times dy square, and Iy is Iy bar plus a times dx square, okay, where dy and dx are the distance between the two parallel axes. Okay, and likewise one can also have what is called as a perpendicular axis theorem. Okay, this is a digression. Okay, typically if you have a composite or if you have some arbitrary shape, I mean, if I go back and bring my other shape from above, just bear with me for a minute. If I go and bring this guy here, I'm just going to copy this and bring it down here. Okay, so if I have this following situation, and if I have my z-axis which is coming out of the page, in this case, okay, so this is my z-axis, this is out of the page. Okay, we have the perpendicular axis theorem, which says that the moment of inertia about the z-axis is going to be the moment of inertia about the x-axis and the y-axis. And if I look at this distance here, okay, so if I call this distance as a distance, let's say r, okay, and let's say that this location is some distance dy and dx, as you know, or if I just call it as x and y, okay, some location x and some y and some x. Okay, then I can immediately see that r square is x square plus y square. Okay, and I can make use of the fact that iz is integral ix, which is y square dA, and integral x square dA. Okay, so this is nothing but integral x square plus y square dA, or integral r square dA. Okay, so and this Iz is sometimes also called as the polar moment of inertia. Okay, and this is typically useful for looking at cross sections of circular bodies in strength of materials. Okay, so the polar moment of inertia is Iz is integral r square dA, is useful for circular elements, circular cross sections in strength of materials. That is when you're doing stress analysis and so on and so forth. Okay. Then we come to one more concept, the moment of inertia of a composite shape. Okay, so concept, moment of inertia of a composite shape. Of a composite shape. This is given as the sum of the moment of inertia of its simple connected shapes. Okay, this is the main concept for composite shapes. Okay, composite shape, moment of inertia. Okay, this is what we will be looking at in terms of problems and so on, and this is what you'll be seeing in strength of materials. Okay, and this employs the parallel axis theorem. Repeatedly. Okay, and that's about it. Now what I want to do is I want to make use of this in a very quick example, okay, and then show you how to calculate the moment of inertia. Okay, so let's look at a problem. I have the following T section, okay, and I'm going to do this a little quickly here so that I won't bore you too much. So I have this T section, and I want to find the moment of inertia of this T section about its centroidal axis. Okay, so here are the dimensions for this T section. Okay, so the top flange of this one is having a width of 100 millimeters. Okay, and then the height of this is 20 millimeters, and this is called as the flange. Okay, this is the top flange, and then this region here, the straight region here, it's typically called as a girder region, or it's also called as a web. Okay, so typically this is called as the web. If I have a bottom piece, then it's definitely called as a web. Okay, and the total height here is going to be given as 80 millimeters. Of course, it's a vertical height given, not an angled height. Okay, 80 millimeters, and the thickness is also 20 millimeters here. Okay, now I want to locate the moment of inertia, or obtain the moment of inertia of the above composite shape, T shape, about its centroidal axis. Okay, so that is the basic idea. Now, what are the steps? I'm going to do a little bit of a hand waving here, because I'm going to make you do some work back when you're looking at this video. Okay, the first step is to locate the centroid of this composite shape. Okay, I'm going to make you do this by yourself, so please do the calculations. Making use of my previous video. On centroid of composite shapes. Okay, so this is something that you'll be doing. And then the second thing is on the composite shape, mark the centroid of each simple connected shape. Okay, so mark the centroid of each simple shape, and then obtain the distance of these from the main centroid of the composite shape. Okay, so this is what you'll be doing next. Okay, and maybe just to have everything down on the same line, I'll just bring this down here, and it'll be a little more seamless. Okay, and then the third step is use the parallel axis theorem. Okay, to obtain the moment of inertia of the simple shapes, of the composite shape, I'm sorry. Okay, so this is exactly what we are going to be doing here. Okay, and here is my T section. I'm going to bring this down one more time here. Okay, with and I'm going to remove some of these things from there. So I'm going to copy that and bring it down here. And here are the things that I want to maybe get rid of for the time being. All of these. Okay, so in my calculations, I chose the following origin. Okay, so I chose my origin in the location as shown, and I want to make sure this is sitting right down there that way. Okay, that's better. So here is my origin. I wrote this as the y-axis, and I had all of these as my x-axis. Okay, which means that my origin is sitting down here, Okay, so based on my origin, okay, the location of the centroid was obtained, centroid of the composite body was obtained as y bar is equal to 32.2 millimeters. Okay, and then x bar, of course it's symmetric, right? So x bar is going to be 50 millimeters. Okay, so here is the centroid, and I want you to check and then see if you obtain the same. I hope you do. Okay, so which means that I'm going to locate the centroid of my shape in the following manner. So it's sitting somewhere here. Okay, and so my dimensions are going to be from here, from my origin, all the way to where this centroid is located. I'm going to call it as the distance y bar. Okay, so this is the distance y bar. Then I'm going to locate the centroid of each of these simple shapes. Obviously the centroid of this simple shape is going to be right there, and the centroid of this simple shape is going to be right down here. Okay, I'm going to give it a different color, of course. Let's make it red color. Okay, so let's make this also red color. All right, so these are the centroids of the simple shapes, and then I'm going to mark these dimensions as y1 bar and y2 bar and x1 bar and x2 bar. Before I do that, I need x bar. Okay, so starting from here, you can obviously see that all of these are coincident, which is really good news for us. Okay, so this distance is going to be x bar is equal to x1 bar is equal to x2 bar. Okay, because all of them are the same. Then I'm going to have y bar, y1 bar and y2 bar. Okay, so starting from my origin here, let me extend this origin here, and all the way to here is going to be y1 bar and then of course y2 bar all the way down to there. Okay, so I need a little more space to write this out. Let's see. I'm going to scoot this down here, scoot that down here, and write this here this way, and then I'm going to take this guy, bring it down here, and then draw a line from this centroid and say that okay, that distance is going to be y2 bar. Okay, so this distance is y2 bar. Okay, then y1 bar and y2 bar, all these distances can be written down, so I'm just going to write the values of these things. Okay, so this is y1 bar, as you can see. Okay, and this I can obtain as a half of the flange width, so this is going to be 10 mm. Okay, y2 bar I can obtain it to be equal to 60 mm. Okay, so this is 60 mm. Y bar was obtained as 32.2 mm. Okay, these were the previous ones that are obtained, and the total length is all seen. Now I start marking the distance between the parallel axes. Okay, I need a different color for that. Okay, so let's say now here is the distance between the parallel axes. I'm going to write these axes down, and I'm going to set up an axis for each of them. Okay, so first of all, look at this. These are going to be, this is going to be the x bar axis for the main one, and this is going to be the y bar axis for the main shape, right? Because this is the centroid of the main shape. Then this is the centroid of the second body, which I'm going to call as C2. This is the centroid of the first body, which I'm going to call as C1. Okay, so this is body 1, this entire thing, if I can shade that out. Okay, and then this is body 2, if I can shade this in a different color. Okay, bear with me. Okay, now this I'm going to call as x2 bar, and then this is x1 bar, and then this is y bar, y1 bar, y2 bar. They are all coincident. Okay, so which means that the distance is available only between the x bar and the x1 bar and x bar and x2 bar. So I'm going to mark this distance here, these two distances from the main centroidal axis. This distance I'm going to call as dy1, dy2. So I hope this makes sense to everybody. Okay, so first of all, I had marked these things. I don't need these anymore. Okay, I can get rid of them. I see that the y bar, y1 bar, and y2 bar are all coincident. Okay, y bar is the centroid of the main composite shape, y bar and x bar. Okay, so let's write this down here. Okay, so x bar and y bar, centroidal axes. For the composite shape. Okay, then x1, y1, x2, y2 bars. These are the centroidal axes for the simple shapes. Of course, these locations are also written here as y1 bar, y2 bar, and so on. So there is a reason for getting confused, but don't be confused by that. These refer to the actual locations. Okay, so these quantities refer to the actual locations. This 10 millimeters, 32 millimeters, and so on. And the other axes that I've drawn are the actual axes themselves. Okay, so this is seen for us. And then I come to the following situation. So I'm going to start writing down the details and so on, okay, on how to calculate the moment of inertia of this entire shape. I'm going to copy this and I'm going to bring it down here, okay, and maybe I'll try to reduce the size of this guy so that we have everything in our perspective. Okay, now first step is the centroid of the main shape. Y bar was 32.2 mm and then x bar is 50 mm from origin O. Okay, then the second step is for each of the individual shapes. Okay, look at the shape number 1, which I'm going to call as 1 here. Okay, the height of that shape is going to be the following. That's going to be 20 millimeters. The base of that shape is going to be the total length of the top flange, which is going to be 100 mm. Okay, the area of the first shape is going to be 20 by 100 mm square. And then dy1 is the distance between the x bar and the x1 bar axes. Okay, so this is going to be y bar minus y1 bar. Okay, so this is going to be 32.2 minus 10, which is 22.2. So many mm. Okay, and dx1 is going to be 0 because the axes are coincident, right? And y1 bar, if you want to write this is going to be 10 millimeters, as you can see. Okay, and then x1 bar is going to be 50 millimeters. This is for the first shape. Then I do the same thing for the second shape. Okay, for the second shape, I'm going to have h2 is the total height, which is 80 millimeters. b2 is going to be 20 millimeters. Then the area is going to be height times the base, so that's 20 by 80 millimeters square. Then x2 bar is the same as x1 bar is the same as x, so that's 50 millimeters. y2 bar is 60 millimeters, as you will be able to see very clearly. Okay, and then I'm going to have dy2. Look at this, dy2 is the distance between x bar and x2 bar, which means that that's the distance between y2 bar and y bar, as you can see. Okay, so this is equal to y2 bar minus y bar. Okay, so this is going to be 60 minus 32.2, so many millimeters. Okay, and then dx2 is going to be 0 millimeters because all of these axes are coincident. Okay, so since y bar, y1 bar, y2 bar axes are coincident. This implies that dx1 is equal to 0, dx2 is also equal to 0 millimeters. Okay, so now how do I find the centroid about the how do I find the moment of inertia about the main centroidal axis? So I'm going to call that as Ix is the moment of inertia, or Ix bar, okay, moment of inertia about centroidal axis x bar. Okay, then this is going to be using the parallel axis theorem, and the idea that Ix bar is going to be Ix1 bar plus Ix2 bar. Okay, or I guess maybe I should specify this a little more clearly. It's going to be Ix bar of the first shape plus Ix bar of the second shape. Okay, so Ix bar of the first shape is the moment of inertia of shape 1, which is the top flange, about the x bar axis, and Ix bar 2 is the same thing, moment of inertia of shape 2, which is the web about the x bar axis. And how do I do this? I make use of parallel axis theorem. So look at this. So Ix bar is Ix bar of the first shape, Ix bar of the second shape. The idea used is the moment of inertia of the composite body is the sum of the moment of inertia of the simple shapes. Okay, so I maybe I want to write this down here. So the idea used here was moment of inertia of composite is equal to sum of moment of inertia of the simple shapes. Okay, then I use the parallel axis theorem because of the fact that the top flange is not coincident with the centroidal axis of the main thing. I have to say the following. So this is going to be Ix1 bar plus A1 times D1 square plus Ix2 bar plus A2 times dy2 square. This corresponds to this, and this corresponds to this one. Okay. Then all I have to do is just substitute. Okay, so substitute for let me maybe write it down one more time. Okay, one more thing is then Ix bar is going to be the following. So Ix1 bar is 1/12 b1 h1 cube plus a1 is b1 times h1 times dy1 square was y bar minus y1 bar square plus 1/12 b2 h2 cube b2 times h2 times y2 bar minus y bar whole square. Substitute for h1 b1 h2 b2 y bar y1 bar y2 bar. Okay, from above we had written all of these things down here. Okay, so I had all of these things here, I had all of these things there, and then just substitute and then plug it in. Okay, this is just a glorified plugging and chugging. Okay, so this gives me Ix bar after calculating it is going to be 12.53 times 10 to the power 6 mm to the power 4. This is the moment of inertia about the x bar axis. Okay, likewise I can say that Iy bar for the main composite shape is Iy bar for the first shape, Iy bar for the second shape. Use the parallel axis theorem. This is going to be Iy1 bar a1 dx1 square, Iy2 bar a2 dx2 square, okay, or iy bar is going to be 1/12 h1 b1 cube. A1 is b1 times h1 dx1 square, and 1/12 h2 b2 cube, b2 times h2 times dx2 square. dx1 and dx2 are 0 for us. Substitute from above, and you will obtain iy bar as 2.31 10 to the power 6 mm to the power 4. Okay, so these refer to the moment of inertia of the entire composite shape about its centroidal axis. Okay, so that's what we are looking at. Okay, so this is the moment of inertia of the composite shape about its centroidal x-axis, and likewise this is the moment of inertia about its centroidal y bar axis, okay, or y-axis. Same idea here. Okay, so I'm going to stop this lecture here because we have gone through a lot of details, and I want this to sink in. But the basic idea is the following. Okay, if I go back and look at many of these things, here is the problem that we started off. It's a composite shape. It's a sum of simple connected shapes. Okay, so first thing is, if I have to find the moment of inertia of this shape about its centroidal axis, first is locate the centroid of this composite shape. This is from our previous video. You can look back at it and see how to obtain centroid of composite shapes. Then locate the centroid of each simple shape and then find its distance from the centroid of the main composite shape. This is exactly what I have marked here as dy1 and dy2 and so on and so forth. Please refer to this figure. Then you make use of the basic idea that the centroid of the composite shape is the sum of the the moment of inertia of the composite shape is the sum of the moment of inertia of the simple shapes with the application of the parallel axis theorem. Okay, which is something that we had used in coming up with these expressions right down here. Okay, so please go through these expressions once again, and I'll have more videos on calculating centroids and moments of inertia for different other shapes very soon. Okay, thank you for your patience, and take care of yourselves. Bye bye.